We've got one more short talk between now and the break. We've heard from Daniel speak about all these interesting innovations. We even have now as experimental browser. We've heard from Patrick talk about OpenFL, how they're moving to Flower. There's really one more big part of the AI ecosystem we need to talk about, and that is foundation models. So I'm going to quickly tell you a bit about what does all of this mean for foundation models and superintelligence. How does it all fit? And to do this, I'm going to start with a bit of a story. Any advance, any big transformative advance takes crazy people. So let me tell you a story about a crazy person. This guy is Burt Munro. He hand-built motorcycles and rode them about 600 miles from here in Utah, the salt flats in Utah, and he started to show people that you could hit speeds with these hand-built motorcycles that no one had ever seen before. He set speed records of 300 kilometers an hour. They made movies about him. Anthony Hopkins played the movie role for Burt. And what the connection here is that Flower is a bit crazy too. Flower has a bit of Burt inside it. And because we've been pushing the envelope to the limit to show that it's possible to train foundation models in a way that's decentralized. The key part to that recipe is to drive down the data movement that occurs during large-scale training. In the last 18 months, we've actually demonstrated with real empirical results that these types of envelope-pushing exercises can drive down the amount of data that needs to be transferred by a factor of 1,000. Now, what this means is this changes everything. No longer does foundation models, no longer does superintelligence have to be the domain of data centers. And that's because data centers and the conventional types of optimizers mean huge amounts of data movement. Because of that, we need to have the data, we need to have the compute, we need to have the nodes all co-located in one tight location, and that means that data centers dominate how we train. But because of what we've been able to show, because we can train these models with far less data movement, it's now looking like this broad set of special kinds of optimizers. You can call them decentralized, you can call them federated. What they essentially are ways of training models that have radically lower levels of synchronization, are enabling us to do things such as outperform consistently long-standing methods such as DDP. But moreover, we're finding these optimizers have other beneficial aspects. They're tolerant to GPU faults. They can keep on training when GPUs start to fail. They're able to cope with asynchronous contributions. They're able to thrive even with hetero versions of GPUs. These are all standard things within a federated system, and yet are very different from a data center. But because these style of optimizers are able to have all of these different types of capabilities, in the long run, where we see these optimizers going, and what we see that Flower is able to deliver, is this ability to train better than DDP, better than anything else, foundation models on data centers, on robots, on cars, on browsers, whatever infrastructure you need, we can deliver superintelligence by adopting and leaning more heavily in to these funky, advanced, exotic forms of optimizers. And so that means that as we start to look into these types of solutions, these federated techniques, as we start to look at the smaller details that come next that prevent them from being used en masse, and we start to nail each of those different types of challenges, we see in the long run that Flower, this open source tool, can become the way that we train all kinds of foundation models, again, irrespective of the underlying infrastructure, all the way from data centers to robots, to cars, to browsers. That's where we're headed. Now, a lot of people can claim a lot of things. You can send out tweets and send pretty good sort of results, right? But I'm telling you, this is real, and it's understandable that you might be skeptical. So let me give you a very hard, clear result. This is some work we did with AMD. They provided us with the GPUs, we provided the know-how, and what you're seeing here in blue is a model, a foundation model that's trained, and we can see over 100 billion tokens of training, we're able to achieve not just perplexity, but downstream performance. This happens to be HelloSwag, that outperforms, in this case, the the open model from the Allen Institute, where we picked the open model so you can give it context of the result we're showing you. So you can see that a model trained with these low synchronization optimizers not only can converge, but they can also provide the types of SOTA level quality that's going to be required for these things to really take off. Again, look at this figure. Over 100 billion tokens trained over, and we're exceeding a centrally conventional DDP-style training recipe. This stuff works. So what does this mean? What this means is, as I mentioned before, the types of infrastructure that you'll see being able to deliver superintelligence is going to explode. It's going to be a much richer set of ecosystems that's built on flower-style technology. We can see, for example, smaller size data centers being networked together to provide the compute and data requirements to build superintelligence. You can see networks of cars and robots. You're going to see networks of user-style GPUs, networks of browsers. Even you're going to see networks of non-AI companies that have data and have unconventional compute working together to deliver the type of superintelligence that they need. This is a huge proliferation of the type of expectations of where we think superintelligence is going to come, and it comes on the back of these styles of federated and decentralized styles optimization. Now, we've known that this has been coming down the pipe for a number of years. So while there exists the standard federated style process that Flower's been known for a number of years, we've built on top of it specific types of extensions that make it brilliant for training LLMs, foundation models, diffusion models, any of these very large scale of training runs. And so what's different about our solution that we can offer people is that it's not only open source. Many of these components have been peer-reviewed and published in places like MLSys and NeurIPS. It supports multimodal training runs. And then I'm happy to announce we're now able to have MOE, so mixture of expert architectures trained under this style of training. As further proof that this is real, let me tell you about the adoption that we've seen. We like to work with partners that want to push the envelope as much as we do. And so let me tell you about our adoption in terms of 1, 2, and 3. 1 stands for the 1 million users that we've been onboarding by cooperating with Varna. Varna is an organization that manages thousands of different data DAOs. So you can see folks contributing their data ranging from Tesla, Fitbit, LinkedIn. They're able to contribute their data, collect it together, and then make conscious decisions of when they start to release it. So we've been onboarding that community onto the type of technology that we've been describing today. And in fact, later today, Anna, who is she's the co-creator of Varna and the CEO of Open Data Labs, is going to join us to describe more about this joint effort. 2 stands for the 2 governments in Europe that are starting to work with us to build cheap, powerful superintelligence by leaning in heavily to the types of optimizations I'm talking about. So we've been working with the German and UK government through this calendar year to show how you can build foundation models using the recipes that I'm describing. And 3 stands for the external 3 foundation models that have been built by entities separate from Flower. So yes, we can train our models, but there's further evidence when you see other research labs starting to train foundation models using these techniques. And so if I just pick one of these, there's a collaboration by UNC Charlotte and Stanford. What they're doing is aggregating massive amounts of eye data and building classifiers that help to detect cancer at a superintelligence level by training them under these federated styles. These folks wouldn't be doing it unless they can deliver models that are obviously at a high quality. And so we're starting to see a coalescence around these Flower primitives of a huge adoption. And so I'm going to close by showing you and introducing one final technical piece of the puzzle. This is a new type of optimizer that we call DesLock. So DesLock is a world's first. DesLock is the first federated, decentralized optimizer that allows training under these extremely low levels of synchronization to occur, but critically, it's provable to converge. And so you can't find this with any other federated style optimizer of the kind that I've been discussing in this talk. DesLock is proven to converge, so it doesn't matter if you train 1 billion, 100 billion, it's going to eventually converge to the result. And so let me show you a result. DesLock is actually able to do extraordinary things. And so let me show you a totally unfair fight. This figure shows on the y-axis complexity, x-axis is wall clock training time, and we're going to compare DesLock to two variants of DDP. One is vanilla, and one has all these different bells and whistles. And so what we see is that under these regimes, this billion parameter model is able to converge for this particular data after about 100 hours of wall clock time for the GPUs we have. And then what we've done here is compared it against DesLock under the exact same conditions, and yet we're using network speeds for DesLock only that are 10x slower. And then we're going to see how long does it take DesLock to converge. What we find is that DesLock is able to outperform DDP and DDP enhanced by 20%, even when it uses links that are 10 times slower. And so this further is a nail in the coffin in terms of any skepticism that these results can work. DesLock is open source, like everything else I've been talking to you today about. And so let me just conclude by saying that I think one of the reasons why we're all in this room today is that the biggest secret in AI, from my perspective, is that tight synchronization between GPUs is no longer necessary for high-quality models. What does this mean? It means, fast forward a few years, we're going to see a proliferation of infrastructure capable of building superintelligence. We're talking, again, as I mentioned before, networks of cars, networks of robots, networks of browsers, networks of data centers working together to build superintelligence. And in this new world, the Flower open source set of tools is ready. It is the de facto standard today for building foundation models under this RAEng. And we're seeing massive adoptions from early adopting research institutions like Stanford, from government-sized institutions like the German government, from forward-looking institutions like Varna with the data DAOs. And so, to conclude, with additions like DesLock, I think the world is finally ready for decentralized training to proliferate. So thank you.